Hello everyone, let's try to be a cheat code ninja today. This problem is a very tricky one because it requires multiple concepts to solve this. Let's have a look at it. We are given a grid of size m rows and n columns, and we are also given an array queries of size k, and corresponding to this queries array we have to generate an answer array where for each query we start at the top left cell, and if the value of the query is greater than the value at that cell, we get 1 point, and we can repeat this process for all the 4 directions: up, down, left, right. Please note that we can get 1 point only once for each cell. And if the value of the query is less than equal to the value at that cell, we do not get any point and we have to end the process. It is also given that we can visit a cell multiple times. And finally, we have to return our answer array corresponding to the queries array. Let's look at an example. The first query is 5. We'll start at the top left cell. 5 is greater than 1, so we'll move right. Similarly, 5 is greater than 2 and 3. We cannot move any further right, so we'll try down. Our current query 5 is not greater than 5 and 7, so we cannot move further down. So we'll again go left, and at 1, we'll start going down. 5 is greater than 2 and 3. We cannot go any further down, so we'll try right. Our query 5 is not greater than 5, so we'll stop. In total, we could collect points only at 5 cells, and we could not go any further because of these cells. Our next query is 6. We'll start at the top left cell. While 6 is greater than the value at the cell, we'll keep going right. We'll try down, but it is not greater than 7. So we'll go left to 2 and then try down. 6 is greater than 5, so we'll go to the last row. Now we'll try the cell at right. Now we'll compare it with 7. We cannot go over there, so we'll go left and then up. So we could cover 8 cells and we could not cover only this cell. For last query 2, we'll start at the top left cell. 2 is greater than 1. But now on both sides, right and down, we cannot go any further. So we get only 1 point. Let's try to come up with an intuitive solution for this. Let's try to understand this question by taking an example where we have only a single query. Our query is 5 and let's initialize our result to be 0. The very first thing that we have to do is start at the top left cell, and if our query is greater than the value at that cell, we have to try all the adjacent cells. And for trying all the adjacent cells, we have to go one step in all the 4 directions: up, down, left, right. And since we are going through the neighbors first, it makes sense to use a breadth first search traversal. We cannot use a depth first search because whether we can move to an adjacent cell depends upon the value of that cell. It does not depend upon the value of a cell which is way farther. Our query 5 is greater than the value at this cell, so we can include 1 point. Now we'll try all the adjacent cells of 1, so we'll go right. Our next cell 2 is smaller than 5, so we'll include a point. Similarly, our query is greater than the next element 3. Now we'll try to go down as we cannot go right any further. Our query is not greater than 7, so we cannot go to that cell. We'll try going back to left. At 2, we'll try to go down. Our query 5 is not greater than 5, so we cannot go to that cell. Now we'll try to go left. And from 1, we'll try to go down. Our query is greater than the next element 2, so we'll include it. Similarly, our next element 3 is smaller than query, so we'll include it. Now we'll try to go right. We see that our query is not greater than the value at that cell, so we'll stop. Now we don't have any more cells that we can go to. We could go through only 5 cells, hence our result is 5. One thing you could notice is that these 3 cells form a boundary because of which we could not go any further. This boundary cuts off the remaining cells from the cells that we could visit from the top left. On the other side of the boundary, there is an element which is smaller than our query, but we cannot visit it. Let's take another example with the query as 2. We'll initialize the result to be 0. Again, we'll start at the top left cell. We see that our query is greater than the value at this cell, so we'll include it. Now we'll try to go right. we see that we cannot go any further because our query is not greater than the value at this cell. We'll now try to go down from our top left cell. We cannot include this cell because our query isn't greater than it. Now we have no more elements we can try on, so our result is 1. Even in this example, you can see that these two cells form a boundary. Even though on the other side of the boundary, there is an element which is smaller than our query, we cannot access it because the boundary cuts it off from the top left cell. Now let's increase our query to 3 and see what happens. Our top left cell is smaller than our query, so we'll include it and start going right. Our next element 2 is also smaller, so we'll include it. But our next right element isn't smaller, so we cannot include it. Now we'll try going down from 2. We cannot access this cell because 5 is greater than our query. Now we'll try going down from 1. We see that 2 can be included. Our next element 3 cannot be included because our query isn't greater than it. Now we have no more cells we can go to, so our result is 3. Even here you could see that these 3 elements form a boundary that cuts off the rest of the grid from our top left cell. One thing you can notice is that when our query increased to 3, all the cells that were included for a lesser query such as 2 were also part of the bigger query. One more thing to notice over here is that in this case, the number of elements which are cut off by the boundary is lesser. Let's try to increase our query to 5 and see what happens. In this case, this will be the boundary, and these two cells which were earlier excluded for our smaller query can now be included. Now let's increase our query to 6 and see what happens. In this case, there is only one cell that we cannot go to, so that will become our boundary. And you can see that there are some elements which were not included earlier are now included. Now let's increase our query to 8 and see what happens. Now the whole grid can be included and the result will be 9. So you can already see that for a bigger query, we can reuse all of the values from a smaller query. Let's try to identify some more patterns on how we can reuse the results for the smaller queries. Let's again take the example of query 5. If we take a look at the cells which are included, all of these cells are less than 5. And for these boundary values in red, we can only pass through it if our query value is greater than it. Please note that even with a query value which is equal to the cell value, we cannot pass through it. We need a value greater than it. So we can consider the cell values as a threshold which the query values must exceed to pass through them. When the query becomes 6, we pass through the threshold of 5 and these cells are now included. All the values in these cells are less than 6. And to include this boundary value 7, our query value must exceed the threshold value of 7. When the query value becomes 8, even now this can be included. One thing to be careful about is that the threshold value of a cell will depend upon the BFS traversal, and we cannot use the cell values directly to determine the threshold. For example, this one at the bottom right cell is smaller than our query 5, but this can be included only when we exceed the threshold value of 5. So for these 3 cells, the threshold value is 5, even though one of the cells is smaller than 5. Let's try to find the threshold value for each cell in the grid. We'll start with the top left cell. We need a value greater than 1 to include it, so its threshold is 1. So far we have found only one element whose threshold is 1. Let's note this down. We'll see how we can use this later. And now from 1 we have 2 neighbors we can go to. The threshold of both of them is 2. Let's note down 2 entries with the threshold 2. Now we have 3 new neighbors we can go to. So we have to decide which element we should visit first. The threshold of the cells with value 3 is 3. So the minimum value required to include it would be 4. On the other hand, the threshold for this cell is 5. So we'll be requiring a minimum value of 6 to enter this cell. But 6 is greater than the minimum value required to pass the threshold of 3. So for 6, all these 3 cells will be included. What we ideally want is to find the minimum threshold required to enter each cell. When we choose a bigger value, it automatically includes the smaller cells which can be opened by a smaller threshold. For example, if we choose a large number, then all the cells in the grid would be included and we cannot find the correct threshold value for any of them. So we should try to include cells as slowly as possible. So when we have unvisited neighbors with different values, we should always pick the cell which has the minimum value. This would ensure that we always get the right threshold value for each cell. So we'll choose the two cells with value 3 and we'll note down two entries with the threshold 3. Now we have two new neighbors 7 and 5. We'd want to pick the cell with the minimum value which is 5. But the problem is, how can we ensure that we always pick the minimum value? We want to avoid a loop on all the neighboring unvisited nodes. Luckily for us, we can use a min heap data structure which would give the minimum of all the unvisited neighboring nodes very efficiently. So in our BFS traversal, whenever we see an unvisited node, we have to add it to our min heap. So now we'll include these two cells. The threshold for them is 5. So we'll make two entries with the threshold 5. Now we have a new neighbor. Its value is lesser than the threshold of 5 we have crossed. So this is immediately available to us and we can include it. To access it, we had to cross a threshold of 5. So even its threshold will be 5. So we'll make another entry with the threshold 5. For the last remaining cell, the threshold is 7. So we'll make an entry with the threshold 7. So let's look at the threshold entries and how we can use them. Since there are 9 cells, we have an entry for each cell, so there will be 9 elements in the array. Let's take the example when the query is 0. In this case, none of the cells can be included because the minimum threshold required to cross the first cell would be 1. So our result is 0. Let's try to derive the same using the threshold entries. One thing you can notice is that the threshold entries will always be sorted in increasing order. This is because in our BFS traversal, we always choose the cell with the minimum value. So the threshold required to include it will be as less as possible. So if we try to insert this query value into our array while maintaining the ordering, it should be at the 0th index. And for any query, it can only include those elements who have a threshold value lesser than the query value. So we should be trying to count the number of elements to the left of its inserted position. In this case, we are inserting it at the 0th position, so there are no entries to the left of it. It means we have no elements whose threshold values are lesser than 0. So our result is 0. Let's try with the query 1. Even in this case, we cannot include any cell because it is not greater than the threshold value required to cross the top left cell. In our array, we already have an entry for 1, but since we are interested in the entries which are lesser than 1, we again find 0 elements. So the result is 0. Let's try with the query 2. In this case, we can only include one cell. We have two entries for 2 in our array, but we are interested in the number of entries which are lesser than 2. There is one such entry, so the result is 1. When the query is 3, these 3 entries can be included. In our array, we are counting the number of entries which are lesser than 3. We find 3 such entries, so our result will be 3. When the query becomes 4, these 5 elements can be included. We don't have an entry for 4 in our array, so it must be added over here. We see that the number of entries lesser than 4 is 5, so our result will be 5. When the query is 6, these 8 elements can be included. We don't have an entry for 6 in our array, so we'll insert it at this position. We see that there are 8 entries to the left of it, so our answer will be 8. Similarly, when the query is 7, we can include these 8 elements. There's an entry of 7 in the array, and there are 8 elements to the left of it. So the result will be 8. When the query becomes 8, all the elements can be included. If we insert 8 to our array, it will be at the last position and there will be 9 entries to the left of it. So the result is 9. To find the position of each query in the threshold entries array, we can do a binary search. There can be two cases when a query is not part of the array. In that case, we'll use the position where it should be inserted, and that index will be the number of elements to the left. And when the query does exist in the array, there can be multiple entries of it. And since we are interested in the entries which are smaller than it, we'll use the leftmost position of that query to find the number of elements smaller than our query. For example, if our query is 5, we find multiple entries of 5 in our array, but we'll use the leftmost one. Its index is 5, and you can indeed see that there are 5 entries smaller than it. The time complexity of this would be, in our BFS traversal, we have to add each cell into our main heap once, and we also have to pop each cell once. The number of cells will be m into n, and the heap size will also be m into n. So this operation would take m into n into log of mn. And for finding our result, for each query, we have to do a binary search on the threshold entries array, which will be of size m into n. So this operation would be q into log of mn, where q is the number of queries. Out of these two, whichever is greater will be our time complexity. And the space complexity would be O of m into n. This is because we have to create a min heap of size m into n. And for generating our result, we are storing the threshold entries in an array of size m into n. Let's implement our solution. Let's keep a variable to store the number of rows and columns. Let's define our min heap where we store three things: the value of the cell and its row and column. Since we have to start at the top left cell, we are going to add its entry to our min heap. For avoiding cycles, we'll keep a hash set to track the visited cells. We'll mark the top left cell as visited. We have to keep track of the threshold entries, so let's define an array for that. It is given in the problem statement that the values in the grid are all positive. We'll keep a variable to track the maximum threshold we have crossed so far, and we'll initialize it to -1. Now we'll do our BFS using our main heap. While there are unvisited nodes in the main heap, we'll pop the cell with the minimum value. We'll get three things: its value, its row, and its column. The threshold required to include this cell would be the greater of the maximum threshold we have seen so far, or the value of this cell. And this will be our maximum threshold. Now we'll add one entry for this threshold. We have to repeat this process for each of the adjacent cells. We can go one cell down, up, right, or left. For going down, we'll add 1 to our current row value. The column will be same. Similarly, for going up, we'll subtract 1 from our row value. For going right, we'll add 1 to our column and keep the row same. And for going left, we'll subtract 1 from our column value and keep the row same. We'll have to check if our new row and column values are not going out of the grid. So both of them have to be positive. We'll also check if our row value is not equal to the number of rows. And similarly, our column value should not be equal to the number of columns. We'll also check that we have not visited this cell before. If any of these conditions match, then we'll skip this row and column. We'll now mark this cell as visited. And finally, we'll add this adjacent cell to our main heap. We'll be storing its value and its row and column. Now we are done with our BFS and we are ready with our threshold entries. Now we have to generate the result for each query. So let's initialize a list to store that. We'll check each query, and corresponding to it, we'll find the leftmost index in our threshold entries array. We'll do a binary search for that, and we'll use an inbuilt library which gives the leftmost index for a number in a sorted array. At the end of this loop, we can return our answer. Let's submit our solution. Our solution is accepted. If you have any doubts or concerns regarding this solution, please mention in the comments. If you thought this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.